talking about electric road systems in the Netherlands.
Welcome everyone, my name is Jose Lopez, and today I'll be presenting our research on the analysis of the market potential of electric road system in the Netherlands. I did this work together with Jasper Bakker and Paul Waus, all the three of us from the University of Groningen. As we all know, the European Union is trying to reduce the carbon emissions of freight transport. For trucks, they have set a few goals. For example, they expect that by 2030, the new trucks will emit 45% less CO2 as compared to 2019. This number is increased over the years until 90% on 2040. This also means for the Netherlands that we are expecting that around between 16 and 24,000 e-trucks should enter into the market in the upcoming years. However, when we look at the current number of electric trucks operating in the Netherlands, we can see that the adoption rates have been underwhelming. As of 2022, only 200 electric trucks have been operating in the Netherlands, which accounts only for 0.3% of the total truck fleet. That number for the tractor for semi-trailer was 0.04%. There are multiple reasons why the adoption of electric trucks has not taken off. Among them is the fact that several transport activities require long journeys. These entail large and heavy batteries, multiple recharging stops, and/or fast charging infrastructure. All these factors ultimately create barriers for the adoption of e-trucks. In this context, electric road system can play an important role in facilitating the adoption of electric trucks. In these roads, the trucks are connected to overhead lines that feed the truck with energy required for the transportation operations and also to charge the battery. When looking at prior work related to the deployment of ERS network in the Netherlands, we put particular attention to the report written by Van Ommeren et al. In 2022. In this report, they assume an ERS deployment in the Netherlands as shown in the figure on the right-hand side. As you can see in this figure, most of the important roads of the Netherlands are being converted into an ERS. The deployment of such a network, in their estimation, was estimated to cost about 7.8 billion. In their analysis, they found out that a positive total cost of ownership was possible for logistics service providers and transportation companies compared to battery electric trucks. This was especially true for transportation activities that involve longer distances or longer range. In their calculations, they assume that all of the ERS is deployed at once. They do not consider different phases in which this ERS would be deployed. Furthermore, in one of their concluding remarks, they mentioned that with a cost of 25 cents per kilometer exclusively related to infrastructure, then the end user will be more likely to adopt the ERS technology for the trucks. Inspired on the report mentioned in the previous slide, we arise with our research question, which is, what is the effect of different ERS network configuration on the market potential of the ERS infrastructure? Our first step in our research was to find out the traffic intensity data of the Netherlands. In this figure, you can see a heat map of the traffic intensity of the different roads in the Netherlands. Green means low intensity traffic, and red means high intensity traffic, and yellow is somewhere in the middle. Based on the data presented on the previous slide, we made a design of 4 different ERS networks. The first 2 ERS networks are presented in this slide. Both these networks are small and they are 200 kilometers long. Each of the networks represents a different philosophy. So the left-hand side network represents the corridor philosophy, while the right-hand side network represents the dense philosophy, which covers a much more narrow geographical scope. In this slide, we present the last 2 designs for the ERS network. These 2 designs are large networks, which each of them having 400 kilometers, and they are an extension of the network presented in the previous slide. So as you can see, the corridor network has a new corridor going from the port of Rotterdam to the east, similar to the original corridor. And then the concentrated network, which is the one presented to the right-hand side, is an extension of the compact network where the geographical scope is expanded to some extent. After designing the 4 different ERS networks for the Netherlands, then we went to look for database about origin-destination flows involved in the Netherlands. We got the Basel database, which is a database that shows trips between zones within the Netherlands and outside the Netherlands per year, and these were particularly specific for heavy transport. In this database, all the regions in the Netherlands and also in the neighboring countries were divided into zones. And for each pair of zones, we have a yearly information of how many transportation flows or how many trips took place. Based on this data, we could then have an estimate of how many different transportation activities would actually benefit of making use of a given ERS network design. What you see in this slide is an example. So in yellow, you have 2 different zones, and suppose that there is a transportation activity between those 2 zones. If we wanted to use the ERS network, we first have to go from the originating zone to the ERS network, which is right now in red, then from the entry point to the ERS network to the exit point, and from the exit point to the centroid of the destination area. Based on these calculations, we can determine how long did the trip drive over the ERS and how much or which fraction of the trip was driven outside the ERS. Making the computations presented in the previous slide for all pair of zones, then we can actually determine whether those trips benefit or not from the ERS network. And based on that, we can also determine what's the adoption potential of a given network. In order to do so, we consider 3 factors, which you can see in the table. So for each of those trips, we determine whether these factors apply or not. And if they apply, then we consider that trip part of the adoption potential of the ERS network. So the first factor is the distance to the ERS network. This is the distance between the originating zone to the ERS network, and also the distance between the destination zone to the ERS network. We consider 3 scenarios, so low, middle, and high scenario. For the lowest scenario, we do not allow that this distance is larger than 30 kilometers, both for the destination zone and for the originating zone. For the highest scenario, where we relax a bit these constraints, then we allow for a 150 kilometer distance between each, the destination zone to the ERS network and the originating zone to the ERS network. The sector factor is the percentage over the ERS network. With this percentage, we want to make sure that a great fraction of the trip is traveled over the ERS network. So for example, in the lowest scenario, 70% of the trip needs to be done within the ERS network. And as we move to the highest scenario, we relax to some extent this condition, and we allow that the trip over the ERS network is at least 50%, meaning that the other 50% could be done outside the ERS, supported by batteries. And the last factor is the willingness to make a detour. And this is basically comparing the distance that a truck, for example, using diesel, would have taken to go from between the 2 zones as compared as the distance when using the ERS. So for the lowest scenario, we allow for very little detour, but for the highest scenario, we allow a long detour as compared to the routes taken using, for example, diesel vehicles. In this slide, you can see part of the results of our analysis. So we can see the 4 different figures representing each of the networks, and in each figure, we can see a heat map. The heat map represents the number of trips captured by the adoption potential of each of the networks. Here, we only do the heat maps for the originating zones of the trips and not for the destination zones. As you can see, as expected, the zones that are captured by each of the ERS networks are the surrounding zones to each of them. When we look at different performance measures, we can start by the kilometers driven in the network. And by this, we refer the total number of kilometers driven in the network on a yearly basis. So when comparing both types of philosophies, we can see that the corridor philosophy outperforms the dense philosophy in both cases, for the small networks and for the large networks. So for example, the double corridor, which has the highest number of kilometers driven in the network of all the networks, has 486.7 megakilometers. That's larger than the 431.5 megakilometers of the concentrated network, which is its counterpart for the dense philosophy. Then for the small networks, we also see the same pattern. So actually the single corridor had a larger number of kilometers driven as compared to the compact network. When it comes to market potential, which we define as the number of trips captured by the network, as compared to the total trips on the Netherlands and with its surrounded neighbors, we can see that the concentrated network has the highest with 6.81%. This also holds true when comparing the compact and the single corridor, since the compact has 3.23% and the single corridor only 2.13%. Yet again, when we compare each of the networks based on the average kilometers per trip of those trips that are part of their adoption potential, we can see, as expected, that the corridor networks have longer trips as compared as to the dense networks. Based on the results obtained in our analysis, we can also take a look at the financial implications that it has for each of the four networks. So in this slide, we're looking for the required user fee per kilometer to make sure that the present value of the project related to deploying the ERS is equal to 0. So in order to do so, we consider the following input parameters or input values. First, we assume a capex of 3.1 million euros per kilometer, and this is considering both ways. We have an OPEX of 2% of that capex, and that's per year. We assume that the ERS network lifespan is 35 years and that the interest rate is 4%. As you can see in the plot, we have on the vertical axis the required user fee per kilometer, and in the horizontal axis, we can see the percentage of the adoption potential that is actually realized. And we make this between 40% and 100%. In the results, you can see that the compact and the single corridor are the networks that require a higher user fee, and the extended version of those networks actually require a much lower user fee. Interestingly, the distance between the single corridor and the compact network is much larger than the distance between the concentrated and the double corridor. We think that this is caused by the synergy effects of extending the compact network. So the compact network allows those zones that were part of the compact network adoption potential to actually reach new destinations once the network is extended to the concentrated one. However, for the single corridor and double corridor, we think that each of the two corridors actually target different markets, and there are no synergies between both networks, which would explain that this philosophy does not scale as well as the dense philosophy. In addition to compare the networks based on their financial viability, we can also use a different dimension. In this case, we use the amount of distance that require battery support. In this slide, you can see two plots. One relates to the concentrated network, and the one on the right-hand side relates to the double corridor network. Each of the plots is a histogram showing the distance requiring battery support with and without ERS. That without ERS is the blue blocks, and with ERS is the orange blocks. As expected, the introduction of an ERS means that the distance required battery becomes much shorter, and therefore the histogram shifts the values toward the left. If we assume that 2 kilowatt-hour consumption per kilometer, then we can say that the reduction in energy consumption from batteries for the concentrated network is 658 gigawatt-hour per year, and that of the double corridor is 732 gigawatt-hour per year. Naturally, the double corridor captures trips that are done within farther away zones, and therefore we also expected that the distance requiring battery support was muchly reduced in this network as compared to the concentrated network. To conclude, we show in our analysis that both design philosophies, in considering this study, involve different trade-offs. The corridor philosophy attracts longer trips, which ultimately leads to a large number of kilometers driven in the network. In contrast, the design philosophy attracts many more trips, but several of those are short trips, which leads towards a lower number of kilometers traveled in the ERS network. For this research, there are multiple research directions that could be taken. One of them could be to address some of the limitations of our study. For example, in our study, we did not consider electricity prices. And as we know, this is a critical factor that could make a difference in the decision of whether or not to adopt the ERS network for truck operators. Another limitation of our study is that we did not include fragmented ERS networks. So for example, the ERS network for every 10 kilometers could have only 7 or 8 kilometers deployed, and the other ones leave them empty temporarily, at least during the early phases of ERS deployment. Finally, another possible research direction based on our limitations is to consider more networks that are different and that consider different routes of the Netherlands, but also networks that are longer. So 400 kilometers was a limited number. What if it's 600 or 800 kilometers? That could also have an effect on our results, and we can see more interesting effects and trade-offs between the two different design philosophies that we propose in this research. Thank you for your attention.
So we do have Jose online. Hopefully we can engage with him with a bunch of questions. Jose, can you hear us?
Yes, can you hear me?
Yes, very well. Thank you for joining us.
Yes, sure.
All right, any questions from the audience? Okay, maybe let me just kick off quickly. Jose, your assumption of 2 kilowatt hours per kilometer, is that based on your own modeling, or where did that come from?
Yeah, we use a source, but indeed, actually, we are writing a paper about it, and the first comment from the reviewer was this, like, where is this number coming from? So yes, we did use a source, but we're gonna make a sensitivity analysis on that number, because I agree, it's yeah, it could be proof, this number, indeed.
Yeah, and in simulations that we did, that David presented on, we got figures up to that, and others have told us it sounds quite high as well, but I think for a limit case, 44 tons, it is a reasonable number to be using. But yeah, I think the more papers there are on simulations, it would be good to compare that.
Yes, yeah, that makes a lot of sense, indeed. That's fair. Yeah. Yeah.
In the light blue shirt?
Has any consideration been given to the fact that the double corridor primarily will benefit people not in the Netherlands, or trucking companies that are operating across the Netherlands into Germany, versus obviously the one that's centered around Amsterdam, Rotterdam, Utrecht will be a particular benefit to internal Netherlands usage, and therefore might be more likely to be encouraging government investment.
Because I'm not sure if you heard that.
Not good enough.
Yeah,
sure.
In a nutshell, the point was the different corridor options. Some of them, like the double corridor option, would benefit more freight that's kind of coming in and out of the Netherlands, whereas the first two options would benefit internal freight more. And what influence might that have on the Netherlands government to support such an initiative?
Yes, indeed. So first of all, when we look at the data that we obtained for the traffic flows, so the data is much more specific for the Netherlands case, and it does include data from the neighboring countries for Germany, but it's much more aggregated. So it makes our computations not so ideal. Yeah, on the other hand, we did find that the corridor network actually outperforms the other network in terms of the number of kilometers traveled. So yeah, that was one of the main that's one of the main limitations for our study. But yeah, and we also think that yeah, it should be there should be a way in which we make a more integrated model, not only focusing so much on the Netherlands, but on a broader scope, so that we also think of an ERS that extends outside of the Netherlands, probably going into Germany, because probably, like you said, the ERS network that we have right now, the Corridor 1, probably it's not matching very well with what Germany would do. And that's something that we will have to tackle in a further study. For now, we took a very Dutch context.